Okay, so moving into projectile motion. Projectile motion is a really common example of two-dimensional motion, and it is two-dimensional motion. It's not three-dimensional motion. So anytime you throw a ball or shoot a bullet or shoot a cannon or throw basketballs, anything like that, is all projectile motion. It's all two-dimensional motion. You have an object that is moving. Obviously it's moving up and down, right? It goes up some and then it comes down some, or even if it just starts from some higher height and then drops to some lower height, you've got this up and down or vertical motion. And so we have a delta y that occurs. We have a y minus y initial. In other words, that's what delta y means. We have usually a final y velocity, instantaneous velocity, and an initial y velocity. And then there's an acceleration, which is caused by gravity. So when we talk about projectile motion, once we let go of the ball, or once we hit the ball with the tennis racket, or once we've once we've shot the cannonball or the bullet, once it's loose, now the only acceleration that exists for that object is gravity. There's no other force acting upon it. And that's what would produce an acceleration. That's sort of jumping ahead to chapter 5. But there's nothing else. There's not a parachute on it, right? There's not a rocket behind it, like a rocket engine or other kind of jet engine behind it. It's just this ball or this cannon or whatever, this cannonball. It's just going out there. And so gravity is acting upon it. And again, a sub y, the acceleration in the y direction, in the y dimension, is downward. And so we say negative, and then g, where g is a positive. Remember that g, in and of itself, when you see the symbol g, that means positive 9.80 meters per second squared. So we have this up and down motion. We also have an over motion. In whatever direction horizontally you throw this, or it gets shot at the beginning, that becomes our horizontal motion, our direction. So x is that way. So we have a delta x minus x naught. And then there's some initial x velocity, which is also the average and the final x velocity. And that's because there's no x acceleration. So we're assuming no air resistance in projectile motion equations. And in the lab I have you do a simulation, and then you add air resistance at the very end to see how big a difference it is. There is air resistance, but not for fairly small things, and it's not a huge issue, especially for fairly small objects. And then things just here near the surface of the Earth, and things don't go that far. The further you go, the more it would make a difference. But we assume that we have no acceleration in the x direction. And if there's no acceleration, then that means that all your x velocities are the same. Whatever x velocity you start with, your object does, that's going to be its horizontal velocity the whole time. That doesn't mean its vertical velocity won't change. Its vertical velocity will change because of gravity, but its x velocity won't. So let's talk about some equations. Back when we did one directional motion, we had 4 equations that we used. We're still going to have those 4 equations, but now we're going to talk about them in 2 dimensions. So the first equation we had was this one. The final velocity was the initial velocity plus the acceleration times time. I've explicitly put the fact that these are vectors now, and now I've written out what those vectors are. Right, the final velocity is an x velocity in the x direction and a y velocity in the y direction. The initial velocities, same thing. We have an initial x and an initial y. And then for the accelerations, I've said, well, we'd have an x part of the acceleration and a y part of the acceleration. But since our ax is 0 for projectile motion, we're going to say, okay, well, that's actually 0. And then our AY being negative G, we'll plug that in as well. Now, the things that happen in the X here, the things that have I hat, they don't mix with the things that have J hat. They can't affect the stuff that's happening in the J hat direction. And so we can combine our I hat terms. In that case, all I have is that the final X velocity is the initial X velocity, which I already knew. So that's not particularly interesting. But what I do get out is that in the J hat terms, I get that the final Y velocity is the initial Y velocity minus GT, which looks very similar to the equation one we had for Y motion, vertical motion, but we've just added these subscripts of Y here, telling us that this is the Y velocity, an initial Y velocity, and there's also an X velocities. So this is not the total velocity, it's just the Y components of them. But that's what we're going to have for our equation 1. We had delta X was equal to 1/2 the two velocities, initial plus final times time. We still have that equation, but now we can write this out officially with the whole vector, where I have my final velocity vector and my initial velocity vector. And again, I can group this by I terms and J hat terms. And what I get when I go through and do that is I get this equation for things that are happening in the X direction, which looks, it's very straightforward here. It just says that the X displacement is equal to the X velocity. And sometimes this is written as V naught X. So sometimes this is V naught X and sometimes it's Vx. It's the same number, so it really doesn't matter. But we could also write this as V naught X or Vx because they're the same thing. If I look at it in J hat terms, I get that the Y displacement is 1/2 the final Y velocity plus the initial Y velocity, the whole thing times time. And that again looks very similar to our equation 2 from the past. It just has these Y subscripts on it. The third equation that we used could also be written in terms of J hat, I hat, and J hats. I get the exact same equation here as I did from equation 2. And this is again because the acceleration in the X direction is 0, we're getting essentially the same equation back over and over again. But the J hat terms give me a different equation. They tell me that Y minus Y naught is equal to V naught Y. So this is our difference here as we put that subscript Y on here times time minus 1/2 G T squared. And that's my equation 3. And then finally our equation 4, which was the V squared is equal to V naught squared plus 2A, it was either X minus X naught is what we had before. If we put in that AX is 0, we just get that Vx squared is equal to V naught X squared, or that Vx is equal to V naught X, which I already knew again. But what I get out from the Y is that Vy, the final Y velocity squared, is the initial Y velocity squared, minus 2G Y minus Y naught. And so again, this looks very similar to what we had back in chapter 2, which was this equation when we just had vertical only motion. We had vertical only motion, V, our final vertical velocity, was the only velocity, but now because we have X and Y velocity, we have to write subscripts of Y on there, and that's why we're seeing these slightly different, because we don't just have X velocity or Y velocity, we have both. So bringing those back together again, our projectile motion equations, the equations you use for projectile motion, we have horizontal equations and we have vertical equations. Really the only equation in the horizontal is that the displacement is equal to the x velocity times time. And sometimes, again, this might be written as v naught x times time or vx times time. They're the same number, and so it really doesn't matter. In the vertical, we do have the 4 equations. We have our 4 equations where there is an acceleration. Remember that in these equations, g is a positive 9.80 meters per second squared. We already have the negative in here. That's telling us that it's acting down. Those subtractions tell me this gravity is acting down. Now all this subscripts of v naught x and v naught y and vy and vx, that's telling me that both v, the initial velocity, and the final velocity have components, right? They have components. So v naught x, so say I shoot something up at an angle like v naught, and here's the v naught for it, and it's at some angle, theta, then v naught x would be this part of it. And so I'd say v naught times the cosine of that, and v naught y would be v naught times the sine of that angle. Or you could have an angle that moves down, in which case this angle would be negative, right? This would be a negative angle down here. Let's see if I can write that someplace else. It's not quite, because it's moving counterclockwise, clockwise to get to that angle. And you could put in a negative angle into this cosine and sine, and you would get out the correct v naught x and v naught y. So this is just going back to the chapter 3 of how to take a vector and split it into its components. V itself, the final velocity, also has some, it could be up. We could have an up, in which case this theta would be positive, or we could have it be down, in which case this theta would be negative. In either case, these would be the equations we would use to get the components of our velocities. Okay, I think I want to do number 21 in this video quickly, and then I'll do 2 more examples in the next video. So let's look quickly at number 21. Blow that thing up. I'll come over here. Okay, so number 21 says a dart is thrown horizontally. So thrown horizontally. If I actually drew this dart and I drew its initial velocity, so here's its velocity, that's horizontal, right? It's all horizontal. So theta here, the angle that this makes with the horizontal is 0 degrees. So thrown horizontally means that the theta of the initial velocity is 0 degrees. So that's the thing to know. There's another one of these words that means a number. It's with an initial speed, so the magnitude of this velocity, this initial velocity, is 10 meters per second. So I'll write that down too. I'll say v naught. The magnitude of it is 10 meters per second. That doesn't even look like, that looks almost like an R. So V naught, the magnitude of it is 10 meters per second. Towards a point P, the bullseye on the dartboard. So actually, let me move this down a little so I can have it go towards my dartboard. So my point P is going to be here, right? And that would be directly opposite this. But my dart actually goes, right, it's going to fall down. It doesn't get to go straight across. So it goes towards the dartboard, but then it actually hits point Q on the rim, which is vertically below P. Right, so that should actually be, I think I took this a little too far. So point Q is going to be here, and it's right below Q. Sorry, right below P. So this is my path that I've tried to draw with my dashed line for what my dart is actually doing. And they tell me that this takes a time of 0.19 seconds to occur. So I release my dart, 0.19 seconds, it hits here. Yeah, so what I'm going to do first is I'm going to sit there and say, well, V naught x is V naught the amount times the cosine of theta, and V naught y is V naught times the sine of theta. And that's always probably, if you've got both your V naught and your angle, it's not a terrible idea to go ahead and do this. Now, I don't even have to do this math specifically, right? I'm looking at this vector, and that's all horizontal. It's all in the x direction. If I put the cosine of 0, I'm going to get 1 times 10, and I'll get that this is 10 meters per second, and this is 0 meters per second if I do the sine of 0. But I can also just sometimes just tell, right? So then it wants to know in part A, what is the distance from P to Q? Now P, this is my initial height, right? This is my initial height here, and Q is the final height, is right there. And so y minus y naught is here, up down to there. This is my y minus y naught. The magnitude of it is the distance from P to Q. So this is what I want to know for part A. So I can sit there and think, okay, I know time, I know V naught y, I want to know y minus y naught. Do I know stuff that can get me that? And so I'll go back and look at my equations, and this is often the way that it is, but this is a very popular equation. Y minus y naught is what I'm trying to find out. V naught y I know, and time I know. And so I can use equation 3 to calculate this. So y minus y naught is 0, that's my initial velocity, minus 1/2 g 0.19 second squared. And if I go and do that math, I get negative 0.177 meters. I get a negative y minus y naught. And that makes sense. I'm starting at a higher velocity, a higher position, and I'm ending at a lower position. So y minus y naught is downward. I get a negative number here because my final height y is less than the initial height. Why not? And that's something you need to remember as you go through and do these calculations, and you do something else. Say you know this, and you've got to plug in y minus y naught instead of finding it. If your object ends up lower than it started, then y minus y naught is going to be a negative number. You need to make sure that you put it in as a negative number. Hopefully we'll do another example where that will become clear why that's so critical. So in this case, though, because we just want to know the magnitude of it, the magnitude or the length from P to Q is 0.177 meters. So that's part A. Now it says, how far away from the dartboard is the dart released? So how far away? So if this is where my dart was released, x naught, then here's x. And so this is what it wants to know now. What is x minus x naught equal to? How far away was I from the dartboard? Well, x minus x naught is really, it's the simplest one. It's v naught x times the time. We know v naught x, and we know time. So our v naught x is 10 meters per second. And that's how fast the x velocity stays the entire time. Now the y velocity changes. We start with an initial velocity in the y direction of 0, but it increases as it falls down. It becomes a negative number. It's in the negative direction, but it's still becoming a larger value. So your dart's actually moving faster in speed as it gets further away from you. Anyways, we'll put in the 0.19 seconds. That's how long it takes. The amount of time it takes for it to go from here in y to here in y is the same amount of time it takes for it to go from here in x to here in x. It's the same amount of time that's going on here. So this is 1.9 meters, or probably just 1.9 meters, two significant figures for part B. Yeah, so looking at these equations for vertical and horizontal motion that occurs with projectile motion, there are the Vy, V naught y, G, these are only in the y equations, and x, x naught, and V naught x, they're only in the x equations, but the time, the amount of time it takes for this object to move in the y dimension is the same amount of time as it takes for it to move in the x dimension. So the only variable, the only physical parameter that is the same or shows up in both of these is time. And typically the time has to be gotten from the y equation if we have to find it. All right, let me pause and do the last video where I'll do 2 more examples.